Okay, so yesterday we talked about bonding in general. Today we're talking about covalent bonding in particular. So remember covalent bonding, what is the deal with the electrons?
They're sharing.
They are sharing. All right, you have covalent bond energies, just like you have any type of bond energies, an average of all the individual bond dissociation energies. It's the amount of energy needed to break a bond. Let's look at this little shrinky-dink table. Okay. When we have a single bond between two carbon atoms, the length of the bond is 154 picometers. The energy required to break that bond is 347 kilojoules per mole. When there is a double bond hooking together two carbon atoms, the bond length is 134 picometers, and the amount of energy needed to break the bond is 614 kilojoules per mole. When there is a triple bond between two carbon atoms, the bond length is 120 picometers, and the amount of energy needed to sever that bond is 832 kilojoules per mole. So you notice the trend. What is the trend? Okay. As the number of bonds increase, the length decreases. As the number of bonds increase, the amount of energy needed to break those bonds increases as well. Okay, so here's what I would like you to know. First of all, bond length decreases as the number of bonds increase. And I'd like to define this term bond order for you. I'm not going to ever use it again, but it occasionally shows up on the AP test, and kids try all this stuff to figure out what the bond order is. The bond order is literally just counting the number of lines between the two atoms. So the bond order is 1, there's 1 line, 2, it's a double bond's 2 lines, 3. Okay, don't lose this very easy recall question point because you didn't recall it. Multiple bonds have higher bond energies. They have higher bond energies because there are more of them. Multiple bonds have shorter bond lengths. They are stronger bonds. They're holding the atoms more tightly together. You know what? I don't really want to go through the change in enthalpy using bond energies. We did that before. Remember, enthalpy is the amount of heat in a reaction. To find the heat in a reaction, what you do is take the sum of the bonds broken minus the sum of the bonds made. Bonds are broken in the reactants, and bonds are formed in the products. So we recall the delta H of the reaction is reactants minus products. It's the weirdo. You either remembered it on the test and were happy, or you forgot it on the test, much to your chagrin. Okay, to solve this problem, it would be nice if you could draw the molecules so you could figure out what the bond energies are. I'm not going to do it because I don't have table 8.4 printed out, so we're just going to leave you to your own devices here. Okay, the next thing I'd like to talk about is the localized electron bonding model. It's a way to visualize covalent bonding. So it's a way to visualize the shared electrons. What electrons are available for bonding?
Valence.
Okay, the valence electrons. So although it is a big name and looks kind of scary, it's the stuff that you learned in Chem 1. It's Lewis dot diagrams. Remember Lewis dot diagrams? Let's take a walk down memory lane. To do a Lewis dot diagram, you simply, for an atom, you wrote the symbol for the atom, and then you placed a dot by the symbol for each one of the valence electrons. Lithium has
1.
done. Fluorine has 7, starting using cardinal points. That means north, south, east, west. you dotted, and then you doubled up when you had to. There you go. Well, that's kind of crookedy, but it's okay.
Really quickly.
Well, it's all right. Okay, now, we're going to use this principle to do our molecule bonding. But first you need some definitions. First of all, a lone pair are electrons that are localized on one atom and not shared. Okay, that's fancy talk for electrons that belong to one atom. And they aren't shared by the molecule. A bonding pair are electrons that are found in the space between atoms and are shared. A bonding pair belongs to both atoms. A lone pair belongs to one atom. There are 3 parts of the model. We're just going to get to part 1 today. We're going to describe the valence electrons using the Lewis dot structure. Tomorrow we're going to predict the shape of the molecule using the Vesper charts. And then the day after, we're going to describe the type of atomic orbitals used by the atoms to share electrons. Stay tuned for this. It's quite fun. All right, turn your paper over. Here we go.
Fun like hard or?
No, actually, it's really easy. It's kind of silly. It's so easy. All right, to draw a Lewis dot structure for a molecule, our goal is to have a duet of electrons for hydrogen, that would be 2, and to have an octet of electrons for all the other, that would be 8 electrons. So these are the steps that you need to take to do this. First of all, you have to predict the location of all the atoms in the molecule. Here's a rule for you. Hydrogen is always at the end. A fancy way of saying at the end is it is a ligand. Hydrogen is always a ligand. The least electronegative atom is the central atom. I will break this rule for symmetry. I will sometimes put the most electronegative atom in the center if the 2 atoms surrounding it are the same. The universe loves symmetry. Carbon is always the central atom. I will not break that rule. Carbon is always the central atom. So you've placed your atoms where you think they go in the molecule. You're going to find the total number of electrons available for bonding. That's the number of valence electrons. You're going to determine the number of bonding pair by dividing the number of electrons by 2. You are going to place 1 bonding pair between the central atoms and the terminal atoms. That's that fancy word ligand. And you are going to dot the remaining electrons around the atoms. I'm going to use a separate piece of paper. I suggest you do the same. You won't be able to pick all of these. Okay. So I would like to draw the Lewis dot diagram for the molecule F2. All right, now my directions say predict the location of the atoms. Well, there are just the 2 F's. I'm going to say that one is the central atom and one is the ligand. It doesn't matter. I call this one as the central atom, therefore this must be the ligand. You can do whatever you want. Second thing I'm supposed to do is find the total number of electrons, valence electrons. I look on the periodic table. Fluorine is in group 17, so it has 7 valence electrons. 7 plus 7 is 14 total electrons, or 7 pair that can either be a bonding pair or a lone pair. It says now place 1 bonding pair between the central and the terminal atom. Okay, did it. I used up 1 of my pair. Now I have 6 pair available to place around the molecule. Always start with the ligands first. Therefore, if the ligands are first, central atom is last. So I said this was my central atom, so here are my dots. 1 pair, 2 pair, 3 pair. So now this is an octet because it has 2, 4, 6, 8 electrons. Now I dot my central, 1, 2, 3. I've used my remaining 6 pair. I have no pair left. And each atom has an octet of electrons, 2, 4, 6, 8, 2, 4, 6, 8. This is a good Lewis dot structure. Let's try carbon tetrachloride. All right, I'm supposed to, what?
Where did the 7 come from?
7 came from the number of valence electrons off the periodic table. Yeah,
When you dot around, will you dot in pairs, or do you?
you dot
one.
in pairs.
Yeah.
Now, some of you who had a different teacher may have done this.
I did that.
I don't want you to do that. When you are writing a Lewis dot diagram for your AP reader, they prefer that you show the non-bonding pairs as non-bonding. This implies bonding. This is non-bonding.
I'm telling this Rodriguez.
You go ahead. Okay, now, I need to place my atoms. I know that carbon is always central. I'm going to place the chlorines around the central atom. Now I'm going to count my valence electrons. Carbon has 4, and there are 4 chlorines, each of which have 7 valence electrons. That's 28 plus 4 is 32 electrons, or 16 pair that must be distributed between the entire molecule to try to satisfy the octet of every single atom. Well, I need to hook the ligands to the central atom. So I've used 4 pair right there. That means I have 12 pair that can satisfy the chlorines. If I look, I see that the central atom is totally content. It has 2, 4, 6, 8. It's ready to go. Doesn't matter where you start. Okay, I've used up the remaining 12 pair in satisfying the octet rule for all of the chlorines. It worked out fine. This is a good Lewis dot structure. Okay, let's try NH3. NH3 needs to be drawn. How shall I draw it?
H is always at the end.
H is always in the middle, so N is the central atom. So I'm going to use a configuration that looks like this. All right. There are 5 valence electrons from nitrogen. Each one of the hydrogen has 1. It's a total of 8 electrons or 4 pair available. I'm going to use a bonding pair to hook the ligands to the central atom. That was 3 of my pair. I have 1 pair left over because the hydrogen only has 1 energy level. It only has an s orbital. It can only take 2 electrons. That's why it always has to be terminal. And it is happy without dots, just a bonding pair line between it. However, the nitrogen would like its full octet, 2, 4, 6. The remaining pair is a lone pair on the nitrogen. 1 more, and then I don't want to do any more. Let's try NH4+. Okay, its configuration is very similar to the NH3, except it has an extra nitrogen, hydrogen. So it has 5 valence electrons from the nitrogen, 1 from each of the hydrogens. What does the charge mean?
Add plus 2. Or take 2 plus.
it lost an electron, so you take an electron away from your total. So you have 5 plus 4 is 9 minus 1 is 8 electrons or 4 pair. So I'm going to use all 4 pair to connect the ligands to the central atom. Central atom's happy, the hydrogen are happy. You need to show that this is an ion, and the way you do that is to encase it in brackets and put its charge on the outer right-hand corner. Okay? You will have some time to practice these, but first we need to talk about exceptions to the octet rule. Wouldn't it be great if everything worked out perfectly every time? It doesn't. So here are some atoms that don't need an octet. They either can do with too few or they can do with more than 8. Boron will bond with only 6 electrons around it. Okay, it'll do it, but it's not really happy about it. And it behaves as if it were electron deficient. It goes around the universe hunting more electrons. And it'll form a complex ion with ammonium that's really hard to mess with, so we won't. Beryllium will also bond with less than 8 electrons. So when you see boron or you see beryllium, you're going to think less than 8.
Is there a specific number for beryllium? Or is it just...
It'll do 3. It'll do 2. No, generally it does 2. Now, we're going to talk about those atoms in period 3 or higher. It's period 3 or higher inclusive, so we're including period 3. That exceeds the octet rule. That means more than 8 electrons around the central atom. When we talk about more than 8 electrons around the central atom, we term that expanding the octet. All right. So we will do that right now by drawing the Lewis dot structure for phosphorus pentachloride. I'm going to put phosphorus in the center and then make a Ferris wheel of chlorines around it. Now I'm going to count my valence electrons. Phosphorus has 5, and there are 1, 2, 3, 4, 5 chlorines, each of which have 7. So that's a total of 40 electrons or 20 pair. Remember, always hook the ligands to the central atom first. That takes care of 5 of them. That leaves 15. And we're going to distribute them amongst the ligands first. Okay. If we look, phosphorus has an expanded octet because it has 2, 4, 6, 8, 10 electrons around the central atom. It is in period 3, therefore it's capable of having its octet expanded. Got it?
Mm-hmm.
Okay, so we are now going, you know what, I just forgot to put these notes anywhere. So you're going to have to actually write these down old school. Oh, really?
Or what now?
You're going to have to write notes like, you know,
What is
normal
writing?
people.
What,
You know, like, take out a piece of paper,
make that Yeah, no.
Write this down because I just forgot about double and triple bonds. You use a double or triple bond when the central atom has too few electrons around it. Remember, we always dot the ligands first.
Yes.
If you have run out of electrons and the central atom doesn't have an octet, you'd use a double or a triple bond. How do you do that? You borrow electron pairs to share, and you borrow them from the ligands. All right, here's an example for you. Carbon dioxide. To place the atoms, carbon will be central and the oxygens would be terminal. Carbon has 4 valence electrons. Each one of the oxygens has 6 and 6 is 12, and 4 is 16 electrons, or 8 pair. I'm going to use 2 of my pair as bonding pair to hook the ligand to the central atom. That leaves me 6 pair to satisfy the octet rule of the oxygens and the carbon. I dot my ligands first. Here's 1, 2, 3. So that oxygen's happy. 1, 2, 3. That oxygen is happy, but carbon is not. The central carbon atom just has 4 electrons, and I run out of electrons. So I will share electrons that were formerly around the ligand. I will share them with the central atom as a double bond. Now when I look, there are 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 electrons around this oxygen, and the carbon is 2, 4, 6, 8. Okay?
Yes.
Thank you. Here is another example. What? I guess. Now we're on camera. Okay, I can write this just as it's written. This is central, this is a ligand, this is a ligand. Hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. That's 10 electrons, or 5 pair. 2 hooking the ligands together. That's going to leave me with 3 pair. This is totally done, so I'm going to start dotting this ligand. 1, 2, 3. And I'm out. This is happy, this is happy, this is not happy.
Not happy.
So I am going to promote the ligand's electrons to a triple bond, and the proper Lewis dot diagram would look like this. So to summarize, if things don't work out perfectly, this is what you do. If you have too many electrons around the central atom, Then you expand the octet. Remember, expand the octet means to put more than 8 electrons around the central. If you have too few electrons around the central atom, then you should consider a double or a triple bond. By sharing the ligand's electrons. Too many, and you should expand the octet. Throw those electrons around the central atom. What is the only thing that you have to worry about expanding an octet?
Period 3.
Has to be in period 3 or higher. Too few electrons around the central atom promote some of the ligand's electrons to a multiple bond.